start today by reviewing about rate of change. So if you guys remember about a linear equation, linear equations were of the form y equals mx plus b. M was the slope, and b was the y-intercept. And another way that we could say slope was the rate of change. And linear equations have what we call a constant rate of change. And the way that that shows up on a graph is by a straight line. And so that's how we knew if an equation had a constant rate of change, is if we had a straight line. So with parabolas, we know we do not have a constant rate of change because it is not a straight line on the graph. And so we need to figure out what is going on with the rate of change. So I'm going to start off with two examples, and we're just going to make some tables. I'm going to fill in these tables for you. Okay, so we're going to look at the rate of change of these quadratics, and specifically, we see the x values are increasing by 1 every time, so I would like to focus more on the y values. And just a little refresher, if I'm looking at the rate of change, I'm really just looking to see, okay, what was the change between those 2 points? So to get from 9 to 4, we go -5, 4 to 1, -3, and I could keep filling this out. And let's just make some initial observations at this point. You see how around the center point, which maybe you'd figure out what that center point is called, our lovely vertex, we have the same quantities of the rate of change, just one is decreasing and one is increasing. So that ties into our increasing, decreasing side of parabola by 5, 3, 1, 1, 3, 5. And as some people were noticing in class today, is that, hey, those amounts are increasing by 2 every time. So that's interesting. The rate of change was not constant, but this column, that's what we call the second rate of change. And the second rate of change is constant. Interesting. Let's look at our other table here. And I see I erased some of it. There we go. Well, if I'm filling out the rate of change, guess what? It's the same thing. Cool. Those quadratic equations have the same rate of change. And it's the same thing where if I was to look at the second rate of change, it is also constant. Okay. I'm going to erase this stuff over here because I want to look at more tables in the same panel here. So example C. Okay, well, let's look at the rate of change here. For these equations, if I was to look at my change, got -10, -6, -2, +2, +6, +10. Okay? And looks like I'm really good at erasing values on this table. So you do the same thing on this side. -10, -6, -2, +2, +6, +10. Oh, would you look at that? It's the same as example C. Let's go ahead and erase that word. All right. Well, let's first talk about the similarities that we have between all of these equations. I see this, that the rate of change is not constant. I see that. Well, if I was to look at the second rate of change of my new equations, oh, interesting. The second rate of change is constant. This idea of a second rate of change being constant, this is very much a calculus idea of tying into derivatives. We're not going to get into that because this is secondary too. But in the future, when you talk about derivatives, I hope you remember this day. Anyway, so, okay, every quadratic has a constant second rate of change, and that is something that I do want us to pick out. Okay, well, something else we can notice here is if I'm just looking, here, let's divide these examples in half for a second. If I'm looking at example A and B, how are C and D different? Or what is the same, what is different? Well, we see what was the same is that the second rate of change was constant, but they're just different values. So now we have to look, well, why do we think it was different? And what I hope that you're realizing as you're looking at the equations is that C and D have an A equals 2 value over here. And A and B have an A value of 1. And it turns out that A value is what's determining the growth factor of the rate of change. And so if you look at all of these numbers, -5 to -10, -3 to -6, -1 to -2, do you see how that rate of change just doubled based on the A value? Turns out if A was equal to 3, you would be seeing -15, -9, -3. This 5, 3, 1, 1, 3, 5 pattern turns out the growth rate of a quadratic equation. And everything gets mirrored around this center point. You see how that's where it changes from increasing to decreasing? Really good at erasing stuff. So the vertex is where everything changes. Shocking, the vertex is the most important point of a parabola. So basically, from the vertex, this is what I want you to take away from this, is that this 1A, 3A, 5A pattern is the rate of change of a parabola. And so I'm going to show you an example of what that looks like on the next slide. And what I'm going to do, I'm going to give you some equations. I'm going to tell you the vertex, because basically if you know the vertex and you have the A value, you should be able to graph. So let's say I was going to graph y equals x minus 1 squared minus 4. And this is a format of an equation of a quadratic you have not seen before. And so I'm just going to tell you that the vertex is +1, -4. And the a value actually shows up in front of the parentheses here. So because there's nothing here, my a value is just 1. And so what I'm going to do is first I'm going to plot the vertex, 1, negative 4. One, 2, 3, 1, negative 4. And what I'm going to do is this growth rate of the 1a, 3a, 5a, I can just plug in my a value. So 1 times a, which a is 1, is just 1. 3 times 1 is 3. 5 times 1 is 5. And I got that just by plugging in the a value there. This describes the movement happening between every coordinate of the y's. So, for example, here's my vertex. Now to get to the next point, I'm going to go over 1, up 1. That was that movement. From that point, over 1, up 3. That was that movement. Over 1, up 5. That was that movement. If I wanted to keep going, you know what it would be? 7, 9, 11. That's how that growth keeps happening. We will not have room to graph all of that. And so I'm going to do that the same on the other side because you know what was down the middle? An axis of symmetry, meaning the same movement happens on either side. So once again, from the vertex, I go over 1, up 1, over 1, up 3, and then over 1, up 5. And now I have my graph shape. And so just to show you, I'm going to show you in red. You don't have to write this down if you don't need it, but I just want you to see where that movement came from. Over 1, up 1. Over 1, up 3. Over 1, up 5. And the same thing happened on the other side. And that's how we graph parabolas. So let's do another example. Okay, once again, I'm going to tell you that the vertex is negative 3, positive 2. And the a value is just right in front here. So my a value is negative 2. So following that pattern, 1 times a, which is 1 times negative 2, is negative 2. 3 times a is 3 times negative 2, which is negative 6. 5 times a, which is 5 times negative 2, is negative 10. So I'm going to start by graphing the vertex. And the difference that a negative makes, let's see, negative 3, positive 2, is that the negative with my a just tells me that my graph is going to open down, and that the movement is a downward movement. So since I have the vertex, I'm going to go over 1, down 2, and that was that movement. From that point that I just plotted, over 1, down 6. Great. And I don't have room on my graph to do the minus 10, so we're not going to worry about it. And I do the same thing on the other side. Over 1, down 2, over 1, down 6. And I'm going to mark that in red like I did on the other one, just so you can see where did that movement come from. Over 1, down 2, over 1, down 6. Same thing on the other side. Over 1, down 2, over 1, down 6. That's all it takes. So this just means if we can find the vertex, that we know how to graph, and that's awesome. So let's talk about the different forms of how we pick out our vertex. Well, what I'm hoping that you were maybe starting to notice, and if you didn't, I want you to start looking at it right now. I want you to look at this equation and my vertex. Equation, vertex. How did I get the vertex from that equation? Well, the equation format that I was using is called vertex form. Here's what this looks like. You're going to want to memorize that. Y equals A times the quantity x minus h squared, and then plus k. The A value is what we call our growth factor, which is determining how the parabola is growing over time. And HK is a coordinate that represents the vertex. So what I'm hoping that you were noticing is that from my equations, to get my vertex, the y coordinate just carried in, the x coordinate, I just switched the sign. So -3 and then +2. And the reason that's happening is because in our definition, this is an x minus h, meaning we need to take the opposite of what's in that parentheses, and that's our definition. Okay. Find the vertex of each equation. Alright, so to find the vertex, all I'm doing, here's my a value right here, but I'm just taking the opposite of this number, so because it's a -6, I'm going to go +6, and then my k value just carries through, and that's what we got. So on the next one, I do the same thing, take the opposite here to make it -5, and my k just drops with. Alright, C and D, well, let's start with part D. My x coordinate, I see, is -6. What about the y coordinate? There's nothing there. Well, the number that represents nothing is 0. So -6, 0. Part C, something similar that I can do. This is like, I can put an x minus 0 in parentheses here. And now it'd be 0, 4. So if you're ever missing a part, just make it 0, and it all works out. Let's talk about standard form. Standard form we have seen a lot from Unit 2, our ax squared plus bx plus c. Okay, once again, a is our growth factor. And to find the vertex, I don't have a nice little h that we can deal with. So I'm just going to tell you that to find the x coordinate of the vertex, I'm going to go -b divided by 2a. And this notation just means we're plugging into the equation. So there's some function notation for you. Alright, so here's an equation. We're going to find the vertex, and if I want to find the vertex, I'm going to need to know what a and b are. So I'm going to still call the x-coordinate of the vertex as h, just because it's a really special value of the vertex. So instead of using x and y, we use h and k just to say, hey, this point is special. So I'm just going to go negative b. Well, b is negative 8, which means negative b is going to be positive 8 over 2 times a. And now I have the x-coordinate of my vertex. Well, to find the y-coordinate, which we're going to call k, I'm just going to plug that, whatever I got for h, into the equation for x. And you can type that into a calculator. That is totally fine. You can also do it by hand if you want. And so our vertex is hk, which is 2, negative 1. So now I just want to put this all together for us. I don't remember what number we're on. Are we on 4? Oh, we're only on 3. Okay. Okay. So remember, all we need to graph are the a value and the vertex. So I can already see that a equals negative 1. So I can calculate what my 1a, 3a, 5a pattern will be. But now I still need the vertex. So to calculate the vertex, I just know the x-coordinate of my vertex is going to be negative b over 2a. So since b is 4, negative b is negative 4 times negative 1. Great, and now the y-coordinate of my vertex, I just need to plug this in. Once again, you're welcome to use your calculator, or you can just do it by hand. Negative 4 plus 8 is 4. Okay. In case you're wondering, notice in this step, the squaring was attached to the 2, not to the negative, which is why it stays at negative 4. So we have our vertex of 2, 1. And now my growth rate, I just go over 1, down 1, over 1, down 3, over 1, down 5. And I do the same on the other side. And that's how we graph quadratics.